Tonight, we travel to a world that should not exist, a planet so intensely heated that its atmosphere behaves more like a stellar furnace than a typical world, a planet whose day side glows at temperatures hotter than some stars in our galaxy, a planet where molecules cannot survive, where metals do not remain solid, and where the boundary between planet and star begins to blur. This is Kelt 9b. It orbits a massive, blue-white star at a distance so close that its year lasts little more than a day. Locked in place by gravity, one hemisphere faces constant, relentless radiation. The other remains in darkness, yet even there, the heat refuses to fade completely. Unlike the quiet worlds of our own solar system, Kelt 9b lives in extremes. Its atmosphere is stripped, reshaped, and chemically transformed by stellar energy. Elements that would form rocks on Earth exist there as vapor. Winds move at unimaginable speeds. The planet is slowly losing mass, stretched and heated by forces that may one day erase it entirely. And yet, it remains a planet. In this calm journey through one of the most extreme environments ever discovered, we'll explore how Kelt 9b formed, why it burns so intensely, what its atmosphere is made of, and what its fate may ultimately be. Not through exaggeration, but through the real physics that govern this remarkable world. So dim the lights, slow your breathing, and let's drift outward, far beyond our solar system, to a place where a planet shines almost like a star. Welcome to Theories Before Sleep. Far beyond our solar system, nearly 670 light-years away in the constellation Cygnus, there orbits a planet that defies our expectations of what a world should be. It is not small, it is not rocky, it does not resemble Earth or even Jupiter in any comfortable sense. It is a gas giant, roughly 3 times the mass of Jupiter. Yet it behaves more like a fragment caught too close to a stellar surface. This world is Kelt 9b. To understand why it is so extreme, we begin not with its temperature, nor with its atmosphere, but with its orbit. KELT 9be circles its host star at a distance of only about 0.03 astronomical units, roughly 20 times closer than Earth is to the Sun. At that proximity, gravity binds the planet tightly, forcing it into a blisteringly fast orbit. One complete revolution takes about 36 hours. A year on Kelt 9b lasts less than 2 Earth days. But orbital speed is only part of the story. The star it orbits, Kelt 9, is not like our Sun. It is a massive blue-white A-type star, far hotter and more luminous. Its surface temperature exceeds 10,000 degrees Celsius. Its radiation output is dramatically stronger than what Jupiter receives from the Sun. So, Kelt 9b does not merely orbit close. It orbits close to something far more powerful than our Sun. Imagine standing on Jupiter and replacing the Sun with a brilliant blue furnace, nearly twice as hot. Then move Jupiter 20 times closer. That is the environment of Kelt 9b. The planet is what astronomers call an ultra-hot Jupiter, a class of gas giants that orbit extremely close to their stars. But even among ultra-hot Jupiters, Kelt 9b stands apart. Its day-side temperature reaches around 4,000 degrees Celsius. That is hotter than many red dwarf stars. It is a temperature at which metals can vaporize, at which molecules break apart into atoms, at which traditional planetary atmospheres cannot behave normally. But before we explore those consequences, it is important to understand how such a world was discovered. Kelt 9b was detected in 2016 using the transit method. One of the most effective ways we find exoplanets, the kilodegree Extremely Little Telescope. Kelt survey monitors large portions of the sky, searching for subtle dips in brightness when a planet passes in front of its star. When Kelt 9b transits, it blocks a small fraction of its star's light. From that dip, astronomers measure the planet's size. From radial velocity measurements, tiny shifts in the star's spectral lines caused by the planet's gravitational pull, they determine its mass. Together, these measurements revealed a massive gas giant, extremely close to an exceptionally hot star. But the real surprise came when scientists calculated the equilibrium temperature, the temperature expected based on the star's radiation and orbital distance. The result was staggering. This was not simply a warm gas giant. It was an object approaching stellar-like temperatures on its day side. And yet, it is not a star. It does not fuse hydrogen in its core. It does not produce its own energy through nuclear reactions. All of its heat is externally driven, a direct consequence of its proximity to Kelt 9. Now imagine the physical implications of that proximity. The intense radiation from the star floods the planet's atmosphere constantly. Ultraviolet light, extreme ultraviolet, and high-energy photons bombard the upper layers, heating them to extraordinary levels. At such temperatures, typical molecular compounds cannot survive. Water vapor dissociates into hydrogen and oxygen atoms. Molecular hydrogen splits into atomic hydrogen. Even heavier molecules break apart. This means that the atmospheric chemistry of Kelt 9b is fundamentally different from what we observe on cooler gas giants. Its atmosphere is not a mix of stable molecules. It is a dynamic, high-energy environment where atoms exist in partially ionized states. Iron and titanium, elements that form solid metal on Earth, exist as vapor in its upper atmosphere. Spectroscopic studies have detected signatures of these metals, confirming that Kelt 9b's atmosphere contains gaseous iron. This alone would make it extraordinary. But temperature is not distributed evenly. Because Kelt 9b orbits so close to its star, tidal forces have locked it into synchronous rotation. One side always faces the star. The other side remains in perpetual night. This configuration creates a dramatic temperature gradient between hemispheres. The day side is exposed continuously to stellar radiation. The night side never sees direct starlight. Yet the night side is not cold. At such high overall energy levels, heat is transported by fierce winds across the atmosphere. Models suggest wind speeds may exceed several kilometers per second. These supersonic winds attempt to redistribute energy flowing from the blazing day side toward the darker hemisphere. But because radiation is so intense, complete equalization is impossible. The planet exists in a state of constant atmospheric motion, driven by extreme temperature differences. Now consider gravity. Despite its high temperature, Kelt 9b remains gravitationally bound. Its mass, nearly 3 times that of Jupiter, provides significant gravitational pull, helping it retain much of its atmosphere despite the intense heating. Yet it is losing mass. Observations indicate that the upper atmosphere is expanding and escaping into space. Hydrogen and other light elements are being stripped away by stellar radiation. The planet is slowly evaporating, not explosively, not dramatically, but steadily. Its atmosphere is extended into a comet-like tail, trailing behind it. This mass loss is measurable, and over long timescales, it may significantly alter the planet's structure. But here is something remarkable. Even under such extreme conditions, Kelt 9b remains stable enough to orbit consistently. Its orbit is not decaying rapidly, at least not on human timescales. It continues its 36-hour cycle, repeatedly passing in front of its star, offering astronomers brief windows to analyze its atmosphere. Every transit provides data. Every spectral observation reveals more about how matter behaves under extreme stellar irradiation. And that is perhaps the most important aspect of Kelt 9b. It is not simply an anomaly. It is a laboratory. At temperatures approaching 4,000 degrees Celsius, atomic processes dominate. The planet allows astronomers to study high-temperature atmospheric chemistry in real conditions. It bridges the gap between planetary atmospheres and stellar atmospheres. It exists at the boundary between planet and star, not because it produces fusion, but because its environment forces it into stellar-like behavior. And yet, it formed as a planet. It likely originated farther from its star, where temperatures were lower and gas could accumulate more easily. Migration processes, gravitational interactions with the protoplanetary disk or other bodies, likely moved it inward over time. This migration would have transformed it from a relatively ordinary gas giant into one of the hottest planets ever observed. Its current state is not its original state. It is the result of orbital evolution. As we begin this journey into KELT 9b, it is important to see it not merely as the hottest planet, but as an example of how planetary systems can produce extremes. Its existence challenges simple models of planet formation. It forces us to reconsider the boundaries between categories. What defines a planet? Is it mass, composition, internal fusion? Kelt 9b reminds us that classification can blur when physics pushes objects to their limits. In the next part, we will turn our focus to the star itself, Kelt 9, and explore why its properties make Kelt 9b so extreme. Because without understanding the star, we cannot fully understand the planet. For now, let your thoughts drift across that distant system. A massive blue-white star, a gas giant orbiting in just 36 hours, one hemisphere locked in relentless radiation, an atmosphere of vaporized metals, a world glowing almost like a small star, and yet still a planet, silently circling again and again in the deep darkness of Cygnus. If Kelt 9b is extreme, it is because its star is extreme. To understand the planet, we must turn our attention to the object it orbits, a star unlike our Sun in almost every meaningful way. Kelt 9 is not yellow, it is not modest, it is not quiet. It is a blue-white A-type star, massive and intensely luminous, with a surface temperature exceeding 10,000 degrees Celsius, nearly twice as hot as the Sun. Color tells the story in astronomy. Cooler stars glow red. Mid-temperature stars like our Sun glow yellow. Hotter stars burn white and blue. Kelt 9 belongs to the hotter category. Its radiation is not just visible light. It emits large amounts of ultraviolet energy. And ultraviolet radiation carries far more energy per photon than visible light. That detail matters enormously for Kelt 9b. But first, consider the scale of the star itself. Kelt 9 is roughly 2.5 times more massive than the Sun and significantly larger in radius. That mass affects everything from its luminosity to its lifespan. Massive stars burn hotter and brighter because gravity compresses their cores more intensely. That compression increases the rate of nuclear fusion. More fusion means more energy output. More energy output means higher surface temperatures and stronger radiation. But massive stars also live shorter lives. The Sun will shine steadily for about 10 billion years. A star like Kelt 9 will exhaust its nuclear fuel much more quickly, perhaps in only a few 100 million years. It is a star that burns fast and fierce. Now imagine placing a gas giant extremely close to such a star. We often compare Kelt 9b's distance to that of Mercury around the Sun. But that comparison underestimates the intensity of the situation. Mercury orbits a relatively moderate star at 0.39 astronomical units. Kelt 9be orbits a far hotter star at just 0.03 astronomical units. Not only is it close, it is close to something far more energetic. Radiation intensity decreases with distance squared. So moving 20 times closer to a star increases the radiation exposure by roughly 400 times. Now combine that with the fact that the star itself is far more luminous than the Sun. The result is staggering. Kelt 9b is not warmed gently. It is blasted continuously by stellar radiation. But the star's influence extends beyond heat alone. Kelt 9 is rapidly rotating. Its rotation period is less than a day, extraordinarily fast for a star of its size. This rapid spin causes the star to become oblate, slightly flattened at the poles and bulging at the equator. And here is where things become even more unusual. Because of this rapid rotation, the star exhibits what is known as gravity darkening. Gravity darkening occurs when a rapidly spinning star has different surface temperatures at different latitudes. The poles, where gravity is stronger, are hotter and brighter. The equator, where centrifugal force reduces surface gravity, is slightly cooler and dimmer. So Kelt 9 is not uniformly bright. Its poles shine more intensely than its equator. Now consider the orbit of Kelt 9b. Unlike most planets in our solar system, which orbit roughly along the equatorial plane of their stars, Kelt 9b follows an unusual path. Its orbit is highly misaligned relative to the star's rotation. It passes over different latitudes during its orbit, sometimes near hotter polar regions, sometimes near cooler equatorial zones. This means the radiation it receives is not perfectly uniform from orbit to orbit. The planet is subjected to subtle variations in stellar intensity depending on its orbital position relative to the star's surface. That complexity adds another layer to its already extreme environment. The star's ultraviolet output also plays a critical role in atmospheric chemistry. Ultraviolet photons carry enough energy to break chemical bonds. When they strike the atmosphere of Kelt 9b, they split molecules apart, a process called photodissociation. Molecular hydrogen becomes atomic hydrogen. Complex compounds cannot survive. The upper atmosphere becomes a plasma-like environment of ions and free atoms. This process contributes directly to atmospheric escape. High-energy radiation heats the upper atmosphere so strongly that it expands. When the expansion becomes sufficient. The outer layers can overcome gravitational binding and stream into space. In the case of KELT-9b, this escape is not minor. Observations show that hydrogen and even heavier elements are being lost. The star is, in a sense, eroding its planet. But there is another subtle factor. Massive stars like Kelt 9 emit strong stellar winds, streams of charged particles flowing outward. These winds interact with the escaping planetary atmosphere. As Kelt 9b loses material, that material does not drift gently away. It is shaped by stellar wind pressure into a trailing structure, somewhat like a comet tail. The planet exists inside a dynamic interaction zone between its own expanding atmosphere and the stellar wind. This interaction can generate shock fronts and further heating. It is not just passive radiation, it is active interaction. Yet despite this hostile environment, Kelt 9b continues orbiting stably. That stability depends on gravity. The star's mass exerts a strong gravitational pull, and the planet's mass ensures it does not disintegrate entirely. But the system's long-term fate is uncertain. Because KELT-9 is massive and short-lived, its future evolution will be dramatic. As it ages, it will eventually expand into a red giant. When that happens, its outer layers will swell outward, potentially engulfing close-orbiting planets. Given Kelt 9b's proximity, it is almost certainly doomed. But even before that phase, tidal interactions may gradually alter its orbit. Though currently stable, small changes over millions of years could cause the orbit to decay. So the star not only defines the planet's present, it likely determines its eventual destruction. There is something deeply instructive about this relationship. In our solar system, Jupiter orbits far from the Sun. It receives modest radiation. It retains a stable molecular atmosphere dominated by hydrogen and helium. But Kelt 9b, despite being similar in mass to Jupiter, behaves entirely differently because of its star. It shows us that planetary identity is not fixed solely by mass or composition. Environment matters, stellar type matters, orbital distance matters. Change the star, and you change the planet. Kelt 9b is not an anomaly because of what it is made of. It is extreme because of where it lives. Its star is too hot, too luminous, too energetic, and too close. And yet, that very extremity provides astronomers with something invaluable. Because the star is so bright and hot, its light passing through the planet's atmosphere during transits produces strong spectral signatures. The intense radiation excites atoms in the atmosphere, making them easier to detect. Iron, titanium, hydrogen all become visible in absorption lines. The star's brightness acts like a backlight, illuminating the atmospheric composition of the planet. In that sense, the star not only creates the planet's extreme conditions, it helps us observe them. Without such a luminous star, detecting these atmospheric details would be far more difficult. So Kelt 9b exists in a delicate balance. Its star pushes it to extremes, strips its atmosphere, heats it beyond ordinary planetary limits, but also reveals it to us. The relationship between star and planet here is not subtle. It is dominant, overwhelming. The star dictates nearly everything about Kelt 9b's behavior, and this understanding prepares us for the next step. Because now that we understand the power of the star, we can examine more closely what that power does to the planet itself, how its day side reaches temperatures hotter than some stars, and what that means for the physical state of matter in its atmosphere. We will move from the star's energy to the planet's response, from radiation to chemistry, from stellar heat to planetary transformation. And in doing so, we will begin to see how Kelt 9b lives at the thin boundary between planet and star. When a planet's day side reaches temperatures of around 4,000 degrees Celsius, familiar ideas about atmosphere begin to fail. On Earth, air is a mixture of stable molecules: nitrogen, oxygen, water vapor, carbon dioxide. On Jupiter, the atmosphere is dominated by molecular hydrogen and helium, with clouds of ammonia and methane drifting in layered bands. But on Kelt 9b, molecules do not behave the same way. At thousands of degrees Celsius, molecular bonds break apart. Hydrogen does not remain paired as H2. It splits into individual hydrogen atoms. Water vapor, if it exists at all, dissociates instantly. Carbon-based molecules cannot survive in their usual forms. Even heavier compounds fragment under relentless ultraviolet radiation. The atmosphere becomes atomic and, in the upper layers, partially ionized. This matters because ionization changes how matter interacts with magnetic fields and radiation. Ionized gases, plasmas, conduct electricity. They respond dynamically to magnetic forces. They can generate complex electromagnetic interactions. Kelt 9b's atmosphere is not simply hot gas. It is a high-energy environment where atoms exist in excited states, continuously absorbing and emitting radiation. One of the most remarkable discoveries was the detection of vaporized iron. Iron on Earth forms solid metal. It melts at about 1,500 degrees Celsius. But on Kelt 9b's day side, temperatures are high enough that iron exists as a gas. Spectroscopic observations during transit revealed absorption lines corresponding to atomic iron and titanium in the planet's atmosphere. This means that in the upper layers, metallic elements are not locked in solid cores. They circulate in vapor form. Imagine a sky where metal is part of the air. This is not poetic exaggeration. It is physically measured. But temperature is not uniform across the planet. Because Kelt 9b is tidally locked, one hemisphere permanently faces the star. That hemisphere receives constant radiation. The opposite hemisphere remains in darkness. Yet darkness does not mean cold. The night side temperature is estimated to be around 2,000 to 3,000 degrees Celsius, still far hotter than lava on Earth. How can this be? The answer lies in atmospheric circulation. At these extreme temperatures, the atmosphere expands significantly. The scale height, the vertical extent over which pressure decreases, becomes large. This expansion allows heat to be transported efficiently across the planet. Winds likely exceed several kilometers per second. These are not gentle breezes. They are supersonic flows of gas attempting to redistribute energy from the day side to the night side. Models suggest that hydrogen dissociation and recombination play a crucial role. On the day side, molecular hydrogen splits into atomic hydrogen, absorbing energy in the process. When this atomic hydrogen is transported to the cooler night side, it can recombine into molecular hydrogen, releasing energy. This process acts as a chemical heat transport mechanism. It is not only winds moving heat, it is chemical reactions storing and releasing thermal energy. In this way, Kelt 9b's atmosphere behaves in a manner more complex than simple hot gas circulation. The physics becomes intertwined with chemistry. And because ultraviolet radiation is so intense, photochemical processes constantly reshape the composition. Upper atmospheric layers are bombarded by photons that break apart atoms and molecules, generating ions. This ionized layer may interact with magnetic fields. If Kelt 9b possesses an internal magnetic field, which is plausible for a massive gas giant, that field could influence atmospheric escape. Escaping hydrogen would follow magnetic field lines, potentially shaping the extended envelope observed trailing the planet. But how stable is this atmosphere? Given the extreme heating, one might expect it to evaporate rapidly. Indeed, Kelt 9bt is losing mass. Observations of hydrogen absorption during transit show that its atmosphere extends far beyond the visible radius of the planet. The outer layers are being stripped away by stellar radiation. This process is called hydrodynamic escape. Unlike the slow Jeans escape that occurs on Earth, hydrodynamic escape resembles a fluid outflow, a bulk movement of atmospheric material driven by heating. Estimates suggest that Kelt 9b may be losing millions of tons of material per second. That number sounds dramatic, yet in planetary terms, it may take billions of years to significantly reduce its mass. The planet is massive enough that evaporation, though measurable, does not immediately destroy it. Still, the loss is real. The star is gradually eroding its companion. Another intriguing aspect involves temperature inversions. On many ultra-hot Jupiters, upper atmospheric layers are hotter than lower layers because of absorption of stellar radiation by metallic species. Kelt 9b appears to exhibit such inversions. Certain atoms absorb incoming radiation at specific wavelengths, heating upper layers and altering vertical temperature structure. This creates atmospheric profiles more similar to stellar atmospheres than typical planetary ones. In some regions, the planet may glow intensely in specific emission lines. It radiates energy back into space, not only as thermal infrared light, but also through atomic transitions. The planet is not passive. It is radiating vigorously. If we could see it directly, it would glow with its own thermal emission, almost like a dim red star. But unlike a star, it does not generate energy internally. All of this heat is borrowed from its host star, and that borrowed energy reshapes its structure. Deep within Kelt 9b, conditions may resemble those of other gas giants. Dense layers of hydrogen compressed under gravity. But the outer atmosphere is transformed. Extreme heating likely inflates the planet slightly, making it larger in radius than a cooler gas giant of similar mass. This inflation is common among ultra-hot Jupiters. The mechanism is still debated, but intense stellar irradiation appears to deposit energy deep enough to expand the planet's outer layers. So, KLT 9b is both massive and somewhat bloated. Its density is lower than it would be in a cooler environment. The star's energy physically alters the planet's size. Another important point is observational. Because the atmosphere is so hot, molecules that typically complicate spectral analysis are absent or dissociated. This makes atomic lines easier to detect. Astronomers can identify individual elements with clarity. Kelt 9b has become one of the best-studied ultra-hot Jupiters precisely because its temperature simplifies certain aspects of spectral interpretation. Iron, titanium, hydrogen all stand out clearly. It is as though the planet's extremity removes ambiguity. At lower temperatures, chemistry becomes complex and layered. At these temperatures, simplicity returns, but only because complexity has been burned away. Now imagine standing in orbit above the dayside. Below, you would see a glowing, incandescent atmosphere. Clouds, as we understand them, would not exist. Instead of ammonia or water clouds, the sky might contain vaporized metals and atomic species. The planet would not be blue or striped like Jupiter. It would likely appear pale, perhaps glowing faintly red from thermal radiation. And across the terminator, the boundary between day and night, supersonic winds would rush, carrying heat into darkness. There is something almost poetic about it. A planet heated to stellar-like temperatures, metal in the air, atmospheric escape streaming into space, chemical reactions storing and releasing heat. Yet it remains a planet, held together by gravity, orbiting steadily. This boundary state between planet and star is what makes Kelt 9b so scientifically important. It challenges models of atmospheric physics. It tests theories of heat redistribution. It informs our understanding of how radiation interacts with gas under extreme conditions. And perhaps most intriguingly, it forces us to rethink what planetary diversity truly means. In our solar system, the range of planetary temperatures spans from the frozen surfaces of outer moons to the scorching plains of Venus. But Kelt 9b exists far beyond that range. It shows that planetary environments can approach stellar conditions without crossing into nuclear fusion. It exists in the narrow territory where gravity prevents collapse into a star, yet radiation pushes the atmosphere to its limits. In the next part, we will explore how such a planet could have formed in the first place, how a gas giant ended up so close to such a massive star, and what its migration history reveals about planetary system dynamics. Because Kelt 9b did not likely begin its life in this inferno, it arrived there, and that journey may be as fascinating as its current state. Before Kelt 9b became one of the hottest known planets, it was simply a young gas giant forming in a protoplanetary disk, and that fact alone presents a puzzle. Massive stars like Kelt 9 are not gentle places for planet formation. They shine intensely even in their youth. Their ultraviolet radiation can evaporate gas from surrounding disks. Their stellar winds are strong. Their lifespans are short. In such environments, building planets, especially large gas giants, becomes more difficult. Yet Kelt 9b exists. To understand how, we must go back to the earliest stages of the system, when Kelt 9 formed from a collapsing cloud of gas and dust. It was surrounded by a rotating disk, the raw material for planets. Within that disk, dust grains collided and stuck together, gradually forming larger bodies, planetesimals, then planetary cores. Gas giants typically require a solid core, perhaps 10 times the mass of Earth, before they can begin rapidly accreting hydrogen and helium from the disk. But that process takes time, and time is limited around massive stars. A-type stars like Kelt 9 evolve quickly. Their intense radiation can disperse protoplanetary disks in just a few million years. For comparison, our Sun's disk likely lasted several million years as well, but under gentler conditions. So for Kelt 9b to exist, it must have formed efficiently. Most astronomers believe it did not form where it currently resides. At only 0.03 astronomical units from its star, temperatures in the early disk would have been far too high for gas to accumulate. Close to the star, volatile materials evaporate. The density structure of the disk makes gas giant formation unlikely at such small distances. Instead, Kelt 9b probably formed farther out, beyond the so-called snow line. The snow line is the region in a protoplanetary disk where temperatures are low enough for volatile compounds like water to freeze into ice. Ice increases the available solid material, making it easier to build large planetary cores. Beyond that boundary, gas giants are more likely to form. So imagine Kelt 9b forming several astronomical units away in a colder region of the disk. There, it could accrete gas and grow to several Jupiter masses. But then something changed. Over time, gravitational interactions began to reshape its orbit. Planetary migration is a common phenomenon in exoplanetary systems. Interactions between a young planet and the surrounding disk can cause the planet to spiral inward. This is known as Type 2 migration for massive planets. As the planet orbits, it creates waves in the disk material. Those waves exchange angular momentum with the planet, gradually altering its orbit. If conditions favor inward movement, the planet drifts closer to its star. This process can occur relatively quickly on astronomical timescales, perhaps within a few 100,000 years. Another possibility involves gravitational interactions with other massive bodies in the system. If multiple giant planets formed, their mutual gravitational influence could destabilize their orbits. Close encounters might fling one planet inward and another outward. In some cases, one planet could even be ejected entirely from the system. Kelt 9b may have undergone such dynamical interactions. Evidence supporting this comes from its unusual orbital alignment. Unlike the planets in our solar system, which orbit in roughly the same plane as the Sun's equator, Kelt 9b's orbit is highly misaligned relative to the star's rotation. This suggests a violent dynamical history. Smooth disk migration typically preserves alignment between star and planet, but strong gravitational scattering can tilt or warp orbits dramatically. Kelt 9b's orbit crosses stellar latitudes rather than following the star's equatorial plane. That misalignment implies that something disturbed it after formation. Perhaps another giant planet once existed in the system. Perhaps close encounters altered orbital inclinations. Over time, tidal forces between the star and planet would have circularized the orbit, smoothing out eccentricity. But they would not necessarily realign it. So Kelt 9b may have experienced a chaotic youth, forming far from its star, interacting with siblings, migrating inward, and eventually settling into the tight, blistering orbit we observe today. But migration itself introduces another question. How did the planet survive moving so close to such a massive star? As it migrated inward, it would have encountered increasingly intense radiation. Its atmosphere would have heated gradually. At some point, evaporation rates would have increased dramatically, yet it remains massive. This suggests that migration occurred relatively early, perhaps before the star reached its current level of luminosity. Young massive stars are not yet as luminous as they become on the main sequence. If Kelt 9b migrated inward during an earlier phase, the environment may have been slightly less hostile. Alternatively, its large mass may simply have provided enough gravitational binding energy to resist rapid evaporation. 3 times Jupiter's mass is significant. Gravity scales with mass, and escape velocity increases accordingly. Even under extreme heating, a sufficiently massive planet can retain much of its atmosphere. So, mass protected it. But even protection has limits. Over hundreds of millions of years, gradual atmospheric escape will reshape it. Yet because Kelt 9 itself will evolve quickly, the long-term evolution of the planet is constrained by stellar timescales. Massive stars age rapidly. In perhaps a few 100 million years, Kelt 9 will exhaust hydrogen in its core. It will expand, becoming a red giant. Its outer layers will swell dramatically. When that happens, Kelt 9b's orbit may lie within the expanded stellar envelope. If so, the planet would be engulfed. Friction with the stellar atmosphere would cause rapid orbital decay. The planet might spiral inward and be destroyed. So the future of Kelt 9b is likely finite. It may not survive its star's evolution. In that sense, we observe it at a particular moment in cosmic time, a relatively brief phase. It is a planet in an extreme environment, orbiting a star that itself will not last long on cosmic scales. This makes Kelt 9b not just extreme, but temporary. Another important aspect of its formation history concerns metallicity, the abundance of elements heavier than hydrogen and helium. Gas giant formation is influenced by the metallicity of the host star and disk. Higher metallicity disks contain more solid material, aiding core formation. Studies of Kelt 9's composition help constrain whether its disk could have supported rapid giant planet formation. Though A-type stars are more challenging to analyze spectroscopically than Sun-like stars, available measurements suggest that Kelt 9's metallicity is not unusually low. That likely helped. Now consider the broader implication. Kelt 9b demonstrates that gas giants can form and migrate even in systems around hot, massive stars. This expands our understanding of planetary system diversity. For many years, exoplanet searches focused primarily on Sun-like stars, but discoveries like KELT 9b show that even hot luminous stars can host giant planets, and not just at large distances, but in extremely close orbits. Its existence forces planetary formation models to account for efficiency and migration in harsher environments. It tells us that planet formation is robust, that even under strong radiation and rapid stellar evolution, disks can produce massive planets, and that gravitational interactions can sculpt those planets into unexpected configurations. When we look at Kelt 9b today, glowing under intense radiation, it is easy to imagine it as something unnatural. But if formed through natural processes, accretion, migration, dynamical interactions, all governed by gravity and physics, its extremity is not magic, it is consequence. In the next part, we will explore how astronomers study this planet in such detail, how transit spectroscopy reveals its atmospheric composition, how instruments detect vaporized metals, and how measurements of light allow us to probe a world hundreds of light years away. Because despite its distance, Kelt 9b has become one of the most precisely characterized ultra-hot Jupiters. And that precision comes from careful observation of tiny changes in starlight, changes that carry the fingerprint of a planet hotter than some stars. When we study a world 670 light-years away, we do not see its surface directly. There are no photographs of Kelt 9b as a globe hanging in space. No spacecraft has visited it. No probe has sampled its atmosphere. Everything we know comes from light, from those variations. Astronomers have, from those variations. Astronomers have reconstructed the physical properties of a planet hotter than many stars. The primary tool for studying KELT 9b is transit spectroscopy. When the planet passes in front of its host star, a small fraction of the star's light filters through the planet's atmosphere before reaching Earth. That thin layer of gas absorbs specific wavelengths of light depending on its composition. Each element leaves a fingerprint, a unique pattern of absorption lines in the star's spectrum. By measuring how the starlight changes during transit, astronomers can identify those fingerprints. This technique requires stability and precision. The planet blocks only a small percentage of the star's light. The atmospheric absorption effect is even smaller, often less than 1 part in 10,000. But modern spectrographs are sensitive enough to detect it. In the case of Kelt 9b, the first surprising detection was atomic iron. When astronomers examined the transit spectrum, they observed absorption lines corresponding to neutral iron atoms in the planet's atmosphere. Iron, not iron oxide, not condensed metallic particles, but vaporized atomic iron suspended in the atmosphere. The temperature was so high that iron existed in gaseous form at high altitudes. This detection was significant for several reasons. First, it confirmed the extreme temperature estimates. Iron requires thousands of degrees Celsius to vaporize. Its presence validated models predicting dayside temperatures around 4,000 degrees Celsius. Second, it demonstrated that heavy elements could be detected clearly in ultra-hot atmospheres where molecular complexity is reduced. Shortly after iron, astronomers detected titanium, another heavy element existing as vapor. The spectral lines were sharp and measurable, and because the star is so bright, the signal-to-noise ratio was high enough to allow detailed analysis. In cooler gas giants, molecules like water and methane dominate atmospheric signatures, but in Kelt 9b's atmosphere, many molecules are dissociated. Instead of molecular bands, scientists observe atomic absorption lines. This simplifies certain aspects of modeling. At these temperatures, chemistry is driven by dissociation and ionization, rather than condensation and cloud formation. Clouds, as we understand them, likely cannot form on the day side. In cooler gas giants, clouds of ammonia, water, or silicates can obscure deeper atmospheric layers. On Kelt 9b, extreme heating likely prevents stable cloud formation on the illuminated hemisphere. The atmosphere becomes relatively transparent at some wavelengths, allowing deeper probing into its structure. But the observations do not stop at transit. There is also secondary eclipse spectroscopy. When the planet passes behind the star, its thermal emission is temporarily blocked. By measuring the combined light of the star and planet before and during eclipse, astronomers can isolate the planet's own emission. Kelt 9b emits significant infrared radiation because of its extreme temperature. It glows, not brightly enough to see with the naked eye, of course, but detectable with sensitive instruments. Infrared observations provide estimates of dayside temperature and energy distribution. They confirm the extreme heating predicted by theoretical models. Beyond composition and temperature, spectroscopy can also reveal wind patterns. As the planet orbits, Doppler shifts in spectral lines can indicate atmospheric motion. If winds are moving toward or away from us, the absorption lines shift slightly in wavelength. In Kelt 9b's case, these shifts suggest high-speed winds redistributing heat from day to night. These measurements allow scientists to infer atmospheric circulation patterns without ever directly imaging the planet. The precision required is remarkable. Shifts measured are often on the order of a few kilometers per second, tiny fractions of light speed, yet they reveal dynamic behavior in a distant atmosphere. Another technique involves phase curve observations. As Kelt 9b orbits its star, the visible fraction of its illuminated hemisphere changes, similar to lunar phases. By measuring changes in total brightness over the orbital period, astronomers can track how heat is distributed across the planet. If heat were perfectly redistributed, brightness would vary smoothly and symmetrically. But observations show asymmetries. The hottest point on the planet is slightly offset from the substellar point, the point directly facing the star. This offset indicates atmospheric winds shifting the hottest region eastward. Even on a world this extreme, atmospheric dynamics shape temperature distribution. The James Webb Space Telescope has begun expanding these observations further. Its infrared sensitivity allows deeper analysis of thermal emission and atmospheric structure. Instruments capable of resolving fine spectral details can refine temperature profiles and chemical abundances. JWST's data help constrain models of energy, transport, and ionization. But beyond the technical methods, there is something profound in this process. All of this knowledge, vaporized metals, supersonic winds, hydrodynamic escape, is derived from light that has traveled 670 years to reach us. A transit lasts only a few hours. During that brief window, the planet's atmosphere imprints its signature onto starlight. From that imprint, scientists reconstruct temperature, composition, motion. It is like reading a code written in photons. And because Kelt 9b transits every 36 hours, observations can be repeated frequently. This short orbital period is advantageous. Frequent transits mean more data, more opportunities to refine measurements. Over time, data sets accumulate, reducing uncertainty. Another advantage is the brightness of the host star. Bright stars provide stronger signals. Dim stars require longer integration times and produce noisier data. Kelt 9's luminosity makes it an ideal laboratory for extreme atmospheric physics. But studying a hot star also presents challenges. A-type stars rotate rapidly, broadening their spectral lines. This broadening complicates precise radial velocity measurements. Yet despite this difficulty, astronomers have successfully measured Kelt 9b's mass and confirmed its planetary nature. And here is an important clarification. Because its dayside temperature approaches that of some small stars, one might wonder if Kelt 9b is closer to a brown dwarf. Brown dwarfs are objects massive enough to fuse deuterium but not hydrogen. They occupy a boundary region between planet and star, but Kelt 9b's mass is below the typical threshold for deuterium fusion. It does not generate internal nuclear energy. Its heat is external. So despite its stellar-like temperature, it remains firmly categorized as a planet. This distinction matters. Temperature alone does not define stellar status. Fusion does. Kelt 9b glows intensely, but it is heated from outside. This reinforces an essential lesson in astrophysics. Categories are based on physical processes, not appearance. A planet can be hotter than a star without becoming one. As observational techniques improve, Kelt 9b continues to serve as a benchmark for ultra-hot Jupiter studies. Each new dataset refines models of atmospheric escape. Each spectral analysis improves understanding of high-temperature chemistry. The planet stands at the edge of what we can measure, not because it is faint, but because its environment is so extreme that familiar models must be adjusted. In the next part, we will explore the deeper internal structure of Kelt 9b. What lies beneath its glowing atmosphere, how extreme heating influences its radius and density, and whether its interior resembles Jupiter at all. Because even as its atmosphere behaves like that of a small star, its core may remain something more familiar. A gas giant shaped by gravity, transformed by radiation, but still fundamentally planetary at heart. Beneath the glowing atmosphere of Kelt 9b, beneath the vaporized iron and supersonic winds, beneath the layers where hydrogen splits into atoms and ultraviolet light tears molecules apart, gravity still rules. No matter how extreme the radiation above, the planet's internal structure is governed by the same fundamental physics that shapes Jupiter and Saturn: mass, pressure, compression. Kelt 9b has a mass nearly 3 times that of Jupiter. That alone tells us something important. At such masses, gas giants are no longer simply puffy spheres of hydrogen and helium. Gravity compresses their interiors significantly. In fact, beyond about 1 Jupiter mass, adding more mass does not increase radius dramatically. The additional gravity squeezes the material inward. Degeneracy pressure, a quantum mechanical effect arising from the Pauli exclusion principle, begins to resist further compression. This is why many massive gas giants have radii similar to Jupiter's, despite having much more mass. Yet Kelt 9b is somewhat inflated. Its radius is larger than expected for a cold, isolated gas giant of the same mass. The reason lies in its environment. Intense stellar irradiation deposits enormous amounts of energy into the planet's outer layers. Some of that energy is transported downward, heating deeper atmospheric regions. This added heat can expand the planet's envelope, increasing its radius. The mechanism behind this inflation is still debated. One possibility is ohmic heating. In highly ionized atmospheres, like that of Kelt 9ba, charged particles move through magnetic fields, generating electric currents. These currents can dissipate energy as heat deeper within the planet's interior. Because Kelt 9b's atmosphere is partially ionized due to extreme temperatures, electrical conductivity may be significant. Interaction between atmospheric winds and the planet's magnetic field could produce additional internal heating. Another possibility involves the transport of stellar energy through radiative and convective processes that alter the thermal balance of the outer envelope. Regardless of the exact mechanism, the effect is measurable. Kelt 9b is less dense than a cold 3 Jupiter mass planet would be. It is not swollen dramatically, but enough that models must account for extra energy input. Now consider the deeper layers. At high pressures, hydrogen behaves in unusual ways. In Jupiter's interior, hydrogen transitions from molecular hydrogen to metallic hydrogen, a phase in which electrons move freely, allowing electrical conductivity similar to metals. Kelt 9b, being more massive, likely contains an even larger region of metallic hydrogen. Deep within its interior, pressure may reach tens of millions of atmospheres. There, temperature and pressure combine to create a dense, conductive fluid. This region may generate a magnetic field through dynamo action, the motion of conductive fluid creating electric currents and magnetic fields. If Kelt 9bd has a magnetic field, it could influence atmospheric escape. Charged particles in the upper atmosphere might follow magnetic field lines rather than escaping isotropically. This could shape the extended envelope detected during observations. Yet magnetic field strength is difficult to measure directly for exoplanets. Indirect evidence must suffice. The interaction between stellar wind and escaping material may provide clues. Now imagine moving downward further. Is there a solid core? Gas giant formation models suggest that such planets begin with a solid core of heavy elements, perhaps 10 to 20 Earth masses, before accreting massive hydrogen envelopes. But over time, that core may partially dissolve into surrounding metallic hydrogen. Under immense pressure and temperature, distinct layers may blur. Some models propose that Jupiter's core is diffuse rather than sharply defined. Kelt 9b may be similar. Its high mass suggests that if a core exists, it may be proportionally smaller compared to its massive envelope. But because the planet formed beyond the snowline, where icy solids were abundant, initial core formation was likely efficient. The intense heating it experiences today does not necessarily penetrate to the deepest layers. Stellar radiation primarily affects the atmosphere and upper envelope. Deep interior conditions are determined more by gravitational compression than by external heating. So while the atmosphere behaves almost like a stellar surface, the deep interior may resemble that of a conventional massive gas giant. There is an interesting contrast here. Externally, Kelt 9b is extraordinary. Internally, it may be somewhat ordinary, at least by gas giant standards. This dual nature makes it fascinating. A relatively standard gas giant core wrapped in an atmosphere, pushed to stellar extremes. Now, consider heat transport within the planet. Gas giants transport internal heat through convection, rising and sinking motions of hot and cool material. But when strong external irradiation dominates, convection can be suppressed in outer layers. In KELT 9b, intense stellar heating may create a radiative zone near the top of the atmosphere, where energy transport occurs primarily through radiation rather than convection. This can alter temperature gradients and influence atmospheric circulation patterns. It also affects how internal heat escapes. All planets radiate residual heat from their formation, but in Kelt 9b, stellar input likely overwhelms intrinsic heat flux. Its internal heat is small compared to the energy pouring in from its star. Another structural effect involves tidal forces. Because Kelt 9b orbits extremely close, gravitational interaction between star and planet is strong. Tidal forces stretch the planet slightly, potentially causing internal friction and heating, similar in principle to tidal heating observed in Jupiter's moon Io. However, Kelt 9b's orbit appears nearly circular, suggesting that tidal dissipation is currently minimal compared to earlier evolutionary stages. But during migration, if the orbit was eccentric, tidal forces could have been stronger, contributing to early heating. Over time, tides circularize orbits and synchronize rotation. Today, Kelt 9b is almost certainly tidally locked, rotating once per orbit. This synchronous rotation shapes atmospheric structure, but does not significantly alter the deep interior. Let us pause for a moment and imagine descending through the planet. Above you, the atmosphere glows faintly from thermal emission. You pass through layers where atomic hydrogen dominates. Deeper still, pressure increases. Hydrogen becomes denser, molecular again in lower regions where temperature is slightly reduced. Below that, metallic hydrogen forms under crushing pressure. Electrons move freely. Electrical conductivity rises. Perhaps magnetic fields are generated, and somewhere at the center, heavier elements concentrate, remnants of the original core. Despite its proximity to a massive star, gravity keeps this structure intact. Even as outer layers expand and evaporate, the core remains bound. But evaporation continues slowly. Hydrogen escapes most readily over billions of years. Could Kelt 9b lose enough mass to transform into something smaller? Possibly. Some theories suggest that extreme atmospheric escape can strip gas giants down to their cores, leaving behind dense, rocky remnants sometimes referred to as Chthonian planets. Whether Kelt 9b will evolve this way depends on timescales. Its host star's lifespan may be too short. Before atmospheric stripping can dramatically reshape the planet, the star itself may expand and engulf it. So Kelt 9b lives in a race against stellar evolution. Evaporation works slowly. Stellar aging works quickly. Which process dominates will determine its final fate. For now, the planet remains massive. 3 Jupiter masses. A dense, compressed interior. An inflated outer envelope. An atmosphere glowing at temperatures rivaling small stars. This layered structure, familiar deep inside, extreme at the surface, makes Kelt 9b a bridge between planetary and stellar physics. It teaches us that appearance can be misleading. A planet can resemble a star externally while remaining gravitationally planetary at its core. In the next part, we will explore the broader implications of KELT 9bd for exoplanet science, what it reveals about the limits of planetary environments, how it compares to other ultra-hot Jupiters, and why its existence reshapes our understanding of what planets can endure. Because Kelt 9b is not merely an outlier, it is a boundary marker, a reminder that the universe often pushes categories to their edges, and sometimes beyond them. When astronomers first began discovering exoplanets in the 1990s, one class of worlds immediately stood out: hot Jupiters. These were gas giants orbiting extremely close to their stars, far closer than Mercury is to the Sun. Their existence challenged classical models of planet formation. Gas giants were expected to form far from their stars, beyond the snow line, not hugging them in tight, blistering orbits. Over time, more hot Jupiters were discovered, then ultra-hot Jupiters. And among them, Kelt 9b emerged as something beyond even that category. To understand its significance, we must place it within the broader landscape of exoplanets. Many hot Jupiters have day-side temperatures between 1,000 and 2,500 degrees Celsius. These temperatures are already extreme compared to anything in our solar system. They are hot enough to melt rock, to alter atmospheric chemistry dramatically. But Kelt 9b pushes well beyond that. Its dayside temperature approaches 4,000 degrees Celsius, nearly double that of many other ultra-hot Jupiters. At those temperatures, the atmospheric chemistry crosses a threshold. On cooler hot Jupiters, molecules such as water vapor, carbon monoxide, and methane are still present. On Kelt 9b, many of these molecules are broken apart into atoms. It occupies the upper edge of planetary temperature distributions, and that edge matters. Planetary science is often about identifying patterns. How does radius depend on mass? How does atmospheric composition vary with temperature? How does stellar type influence planetary properties? Kelt 9b sits at the extreme end of these relationships, helping define their limits. For example, radius inflation appears to correlate with stellar irradiation. Hot Jupiters exposed to higher radiation levels tend to have larger radii than expected. Kelt 9b, receiving enormous radiation, exhibits this inflation clearly. Its radius is larger than that of a cold 3 Jupiter mass planet would be. Studying it helps refine models of how energy deposition expands planetary envelopes. Another boundary concerns atmospheric escape. Many hot Jupiters lose mass through hydrodynamic escape, but Kelt 9b demonstrates escape under the most intense conditions yet observed. Its atmosphere is not only heated, it is ionized. The escape process involves atomic hydrogen, heavy metals, and interaction with stellar wind. By analyzing Kelt 9b, scientists test the upper limits of atmospheric stability. How much radiation can a planet withstand before it is stripped away entirely? At what mass does gravity win? Kelt 9b suggests that even extreme heating does not immediately destroy a massive gas giant. Gravity remains powerful, but if the planet were less massive, perhaps Jupiter mass or smaller, the outcome might be different. So Kelt 9b informs us about survivability. It helps define which planets can endure extreme proximity to luminous stars. Another broader implication concerns stellar type. Most well-studied exoplanets orbit sun-like stars or cooler, hot, massive stars like Kelt 9 were once thought less likely to host close-in planets. Their intense radiation and short lifespans made detection difficult and formation uncertain. Yet Kelt 9b proves that even massive A-type stars can host ultra-close gas giants. This expands the diversity of planetary systems we consider possible. It also forces theoretical models to account for planet formation in disks around hot stars. Disks around A-type stars are hotter, more luminous, and possibly short-lived. Yet they can still produce massive planets that migrate inward. This realization broadens our view of where planets can form. Now consider the boundary between planets and brown dwarfs. Brown dwarfs occupy a mass range between about 13 and 80 Jupiter masses. They are too small to sustain hydrogen fusion, but can fuse deuterium. Kelt 9b, at about 3 Jupiter masses, lies far below that threshold, yet its dayside temperature approaches that of some brown dwarfs. This decoupling of temperature and internal fusion is crucial. Kelt 9b demonstrates that surface temperature alone cannot determine an object's classification. A planet heated externally can reach stellar-like temperatures without becoming stellar internally. This has philosophical implications. It reminds us that categories in astronomy are rooted in physical processes, not appearances. Fusion defines stars, not temperature. In some ways, Kelt 9b acts as a natural experiment in atmospheric physics. Because molecules dissociate at high temperatures, the atmosphere becomes dominated by atomic species. This simplifies some aspects of spectral modeling while complicating others. It bridges planetary atmospheres and stellar atmospheres. In stars, atomic absorption lines dominate. In planets, molecular bands are often more prominent. Kelt 9b sits between those regimes. Studying it helps unify models of radiative transfer across temperature extremes. Now compare it to other ultra-hot Jupiters. Planets like WASP 33b, WASP 121b, and HATP 7b also exhibit extreme irradiation. Some show evidence of temperature inversions caused by absorption of stellar radiation by metallic species. Some exhibit atmospheric escape. But Kelt 9b remains among the hottest known. Its host star's temperature pushes it beyond most peers. By comparing these planets, astronomers identify trends. How does host star temperature correlate with atmospheric composition? How does orbital distance influence wind speeds? How does mass affect evaporation rates? Kelt 9b anchors the high end of these relationships. Another area of importance involves habitability boundaries. Clearly, Kelt 9b itself is not habitable, but understanding the limits of planetary survival informs broader questions about habitable zones. If planets can exist this close to massive stars, then planetary systems may be more resilient than once thought. Even extreme environments do not preclude planetary existence. They only redefine planetary character. There is also an observational benefit. Ultra-hot Jupiters are easier to study in some respects because their atmospheric signals are strong. High temperatures create pronounced spectral features. Short orbital periods allow frequent transits. Bright host stars provide high signal strength. So while they are rare and extreme, they are valuable laboratories. They allow refinement of techniques that can later be applied to smaller, cooler planets. Every improvement in modeling atmospheric escape on Kelt 9b strengthens our understanding of atmospheric loss on Earth-sized planets orbiting red dwarfs. Every improvement in understanding ionization and radiative transfer enhances our ability to interpret spectra of distant worlds. In this sense, Kelt 9b contributes indirectly to the search for habitable exoplanets. Extreme worlds teach fundamental physics. Fundamental physics informs broader exploration. There is also a temporal aspect. Because Kelt 9's lifespan is relatively short, the window during which such extreme planets exist may also be limited. As the star evolves off the main sequence, its radiation environment will change. Close-in planets may be engulfed or destroyed, so systems like KELT 9b may represent transient phases in planetary system evolution. We are observing it during a particular chapter. Millions of years earlier, it was cooler and perhaps more typical. Millions of years later, it may be gone. This transience adds to its scientific importance. It allows us to study planetary behavior under conditions that will not persist indefinitely. Now imagine a broader survey of the galaxy. Billions of stars, billions of planets. Among them, there will be rare combinations of mass, orbit, and stellar type that create extreme cases. Kelt 9b is one such case. It is not representative of most planets, but it defines the upper edge of planetary temperature. It demonstrates that the universe permits worlds at the brink of stellar behavior without crossing into fusion. It is a boundary object, a world that forces us to ask, how hot can a planet become? How much radiation can it endure? How close can it orbit a massive star and remain intact? In the next part, we will turn toward its future. We will examine how stellar evolution will reshape the system, how atmospheric escape may alter the planet's mass over time, and what ultimate fate awaits a gas giant orbiting so close to a star that burns bright and fast. Because Kelt 9b's present is extreme, but its future may be even more dramatic. If Kelt 9b already seems to sit at the edge of what a planet can endure, the natural question becomes, is this the limit? Or could there be worlds even hotter, even closer, orbiting stars even more extreme? To answer that, we must consider not just what we have observed, but what physics allows. Kelt 9b's temperature is determined by three main factors: the luminosity of its host star, its orbital distance, and how efficiently it redistributes heat. Increase stellar luminosity, move the planet closer, or reduce heat redistribution. An equilibrium temperature rises. But there are constraints. Planets cannot orbit arbitrarily close to their stars without being torn apart by tidal forces. There exists a minimum safe distance known as the Roche limit. If a planet crosses this boundary, tidal forces exceed its self-gravity and it begins to disintegrate. Kelt 9b orbits very near that limit. Its orbital period of 36 hours places it extremely close to gravitational instability. So while it is possible in principle for a planet to orbit even closer, the window becomes narrow. Another constraint is mass loss. At sufficiently high temperatures, atmospheric escape accelerates dramatically. If heating exceeds a certain threshold, the planet may lose mass faster than it can retain it. Smaller planets would not survive long under Kelt 9 like irradiation. But what about more massive stars? O-type stars, for example, are even hotter and more luminous than A-type stars. However, they are rare and short-lived. Their intense radiation and stellar winds make planet formation more difficult. And because they live only a few million years, the window for stable planetary systems may be brief. So while hotter planets are theoretically possible, the combination of formation efficiency, migration timing, and stellar lifespan narrows the field. Kelt 9br may not be the absolute upper temperature limit for planets, but it likely sits near it. Now consider detection bias. We detect planets primarily through transits and radial velocity. Transit detection favors short orbital periods. Radial velocity favors massive planets close to their stars. Ultra-hot Jupiters are relatively easy to detect compared to small, distant planets. So the fact that Kelt 9b is among the hottest known may partly reflect observational sensitivity. There could be hotter planets that simply orbit stars less conducive to detection. But observational surveys have grown extensive. Space telescopes like Kepler and TESS have monitored vast regions of the sky. Ground-based surveys have identified thousands of close-in giants. The absence of dramatically hotter confirmed planets suggests that extreme cases like Kelt 9b are rare. This rarity tells us something about planetary system architecture. It suggests that while migration can bring gas giants close to their stars, there are natural stopping points, perhaps due to disk truncation, magnetic interactions, or tidal forces. Kelt 9b's orbit may represent one of those stopping points. Now let us think about instrumentation. The study of Kelt 9b represents a milestone in atmospheric characterization, but it also previews what future telescopes may achieve. The James Webb Space Telescope already provides unprecedented infrared sensitivity. It allows measurement of emission spectra with higher precision than ever before. Future observatories, such as the Extremely Large Telescope, ELT, on Earth, will offer even greater resolving power. With high dispersion spectroscopy, astronomers will measure atmospheric winds, chemical abundances, and temperature gradients with improved clarity. For Kelt 9b, that means refining our understanding of ionization levels, metallic abundances, and vertical atmospheric structure. But beyond Kelt 9b, these tools will expand exploration to other extreme worlds, hotter stars, closer orbits, different compositions. Each discovery will fill out the high-temperature end of the planetary spectrum, and that spectrum informs fundamental astrophysics. For example, the study of Kelt 9b's atmosphere contributes to radiative transfer theory, how light interacts with hot gas. That same physics applies to stellar atmospheres, accretion disks, and even supernova remnants. Extreme exoplanets are laboratories not only for planetary science, but for broader astrophysical processes. There is also an important conceptual shift here. For centuries, our understanding of planets was based solely on our solar system. Gas giants were cold and distant. Rocky planets were warm and inner. Stars were clearly distinct from planets. Exoplanet discoveries shattered that simplicity. Hot Jupiters orbit closer than Mercury. Super-Earths blur the line between terrestrial and Neptune-like bodies. And KELT-9b demonstrates that planets can approach stellar temperatures without becoming stars. It forces us to refine definitions. Planetary science is no longer solar system science. It is a discipline of diversity. Now imagine looking at KELT-9b from a great distance. The star shines blue-white. The planet, though small relative to the star, glows faintly from its own heat. It completes an orbit every 36 hours, racing through space at tremendous speed. Its day-side atmosphere shimmers with atomic metals. Its night side remains incandescent. Hydrogen escapes in a thin envelope, trailing into space. And yet, gravity binds it. It persists. There is a lesson here about stability under extremes. Even in environments that seem hostile beyond imagination, structure can endure. Planetary systems can host worlds that defy comfortable expectations. They can survive intense radiation, violent migration, and extreme chemistry. And by studying them, we expand our understanding of what the universe permits. In the next part, we will consider the long-term future of Kelt 9b. Not just atmospheric escape, but stellar evolution. What happens when its host star begins to expand? How does a gas giant respond to a star that grows larger and brighter? Because while Kelt 9b today is one of the hottest planets known, its future may involve even more dramatic transformation. Its current state is extreme, but it is not final. The story continues, written in gravity and fusion, unfolding across millions of years beyond our own timescale. And somewhere in Cygnus, that distant system continues its quiet orbit, star blazing, planet circling, unaware that across 670 light years, we are studying it in detail, trying to understand the limits of what a planet can be. Kelt 9b, as extreme as it is today, exists within a system that is still evolving. Stars are not static objects. They change over time. They consume fuel, alter internal structure, expand, brighten, and eventually transform into entirely different states. To understand the ultimate fate of Kelt 9b, we must look not at the planet alone, but at the evolutionary trajectory of its host star. Kelt 9 is a massive A-type star. Mass determines destiny in stellar evolution. The more massive a star is, the faster it burns through hydrogen in its core. The faster it burns, the shorter its lifespan. The Sun, with moderate mass, will remain on the main sequence for roughly 10 billion years. Kelt 9 will not. Estimates suggest that stars of its mass remain stable for only a few 100 million years before exhausting core hydrogen. That is brief on cosmic timescales, and that brevity matters deeply for Kelt 9b. As Kelt 9 ages, hydrogen fusion in its core gradually alters the star's internal balance. Eventually, hydrogen becomes depleted. The core contracts under gravity. Outer layers respond by expanding outward. The star will swell into a subgiant and later into a red giant. Its radius will increase dramatically. Its luminosity will rise. Its outer atmosphere will expand into regions currently occupied by close-in planets. Kelt 9b orbits at just 0.03 astronomical units. That is extremely close. When Kelt 9 expands, the star's outer envelope may engulf that orbit entirely. If that occurs, the consequences are severe. The planet would enter the stellar atmosphere. Drag forces would cause rapid orbital decay. Friction between planetary atmosphere and stellar envelope would generate enormous heat. Within a relatively short time, perhaps thousands or tens of thousands of years, the planet could spiral inward and be destroyed. This scenario is not speculative. Models of stellar evolution predict such engulfment for many close-in planets around evolving stars. Hot Jupiters around Sun-like stars may face similar fates billions of years from now. But for Kelt 9b, the timeline is compressed. The star's higher mass accelerates everything. It may face engulfment within hundreds of millions of years. Compared to Jupiter's multi-billion-year future around the Sun, that is brief. Now consider atmospheric escape over that time. As Kelt 9b continues to orbit its star, intense ultraviolet radiation drives hydrodynamic escape. Millions of tons of hydrogen may leave the planet each second. But even at such rates, stripping away several Jupiter masses requires enormous time. If the star evolves before evaporation removes most of the atmosphere, engulfment will dominate the planet's fate. In other words, stellar evolution may outpace atmospheric loss. There is also tidal interaction to consider. Close-in planets experience strong gravitational coupling with their stars. Over time, tidal forces can transfer angular momentum between star and planet. If the star rotates more slowly than the planet orbits, tidal interactions can cause orbital decay. But Kelt 9 rotates rapidly. In fact, it rotates in less than a day. Its rotation period is shorter than Kelt 9b's orbital period. This creates an unusual dynamic. If the star spins faster than the planet orbits, angular momentum transfer can, in principle, push the planet outward slightly. However, the details depend on internal stellar structure and tidal dissipation efficiency. In massive, rapidly rotating stars like Kelt 9, tidal dissipation may be weaker than in Sun-like stars. So while tidal evolution is present, it may not dramatically alter the orbit before stellar expansion begins. Still, over millions of years, small changes accumulate. Orbital decay or expansion could shift Kelt 9b's position modestly, but given its proximity, even slight decay could hasten engulfment. Now imagine the final stages. As the star expands into a red giant, its surface cools and reddens, but luminosity increases significantly. The planet's dayside temperature, already extreme, could rise further. Radiation increases. Atmospheric escape accelerates. If the planet remains outside the stellar envelope temporarily, it may experience its most intense heating phase during stellar expansion. Its atmosphere could become even more extended. Mass loss may spike dramatically. Eventually, the star's expanding envelope overtakes the orbit. Once inside, the planet encounters dense stellar gas. Drag reduces orbital energy. Spiral in begins. Energy released by orbital decay may even influence the star's envelope structure. Some models suggest that engulfed planets can deposit angular momentum into stellar envelopes, potentially affecting rotation rates or mass loss processes. But for the planet itself, survival is unlikely. It may dissolve entirely within the stellar atmosphere, or its core, if sufficiently massive, could survive briefly before disintegration. The destruction of close-in gas giants during stellar evolution is expected to be common across the galaxy. We may observe signatures of such events indirectly. Some red giants show unusual chemical abundances or rotation rates that may hint at past planet engulfment. Kelt 9bi may one day contribute to such phenomena. There is another intriguing possibility. If Kelt 9b loses significant atmospheric mass before engulfment, could it leave behind a dense core? Some theories propose that evaporated gas giants can transform into smaller rocky remnants, Chthonian planets. However, for a planet as massive as Kelt 9b, stripping away nearly 3 Jupiter masses before stellar expansion seems unlikely. The timescales favor engulfment while still massive. So Kelt 9b's future likely ends not as a rocky remnant, but as material absorbed into its star. Now consider the broader implications. Planetary systems are not static. They evolve alongside their stars. We often imagine planetary orbits as stable for billions of years, but in reality, many systems experience dramatic changes. Close-in planets are especially vulnerable. Kelt 9b offers a preview of planetary mortality. It shows us a world living near the edge of survivability, bound to a star that itself is racing toward transformation. In the long arc of cosmic time, Kelt 9b's current state is fleeting. It formed in a protoplanetary disk, migrated inward, heated to stellar-like temperatures. Now it circles rapidly in an extreme environment, and in the future, it will likely be consumed. This cycle, formation, migration, extreme heating, destruction, may occur in countless systems across the galaxy. We simply happen to observe one example in detail. There is something profound in that awareness. Across 670 light-years, photons carry the story of this distant planet. They tell us about vaporized iron, atomic hydrogen, supersonic winds. They tell us about gravitational binding and atmospheric escape, and they allow us to foresee a future in which the planet no longer exists. Astronomy often stretches perspective beyond human scales. Millions of years compress into models and equations. But in reality, Kelt 9b continues its orbit tonight. It completes another revolution every 36 hours. It glows under relentless radiation. Its atmosphere expands slightly, escapes slightly. Its star burns hydrogen steadily, inching toward a future expansion. All of this unfolds slowly, quietly, beyond our immediate perception. In the next and final part, we will step back and reflect on what Kelt 9b ultimately represents, not only as an extreme exoplanet, but as a marker of how far planetary science has come and how much broader our concept of planet has become in just a few decades. Because Kelt 9b is not only a world warmer than some stars, it is a reminder that the universe rarely conforms to our initial expectations, and that the boundaries of possibility are often wider than we first imagine. When astronomers first pointed their telescopes toward the stars in search of planets, they expected to find variations of what they already knew: rocky inner worlds, gas giants farther out, orbits aligned neatly with stellar equators. Instead, the universe revealed something far more diverse: hot Jupiters hugging their stars, super-Earths with no solar system equivalent, planets orbiting pulsars, worlds with densities lighter than cork and others denser than iron. And among all of them, Kelt 9b stands as one of the clearest reminders that planet is not a narrow category. It is a broad one. Kelt 9b forces us to confront a simple but powerful truth. A planet can be hotter than some stars and still remain a planet. For centuries, temperature was intuitively linked to classification. Stars were hot and luminous. Planets were cool and reflective. Kelt 9b dissolves that intuitive boundary. Its day side reaches nearly 4,000 degrees Celsius, hotter than many red dwarfs. Yet it produces no fusion in its core. It shines not because it generates energy, but because it absorbs and re-emits it. Its identity is defined not by how it looks, but by how it works. And that distinction is essential in astrophysics. Fusion defines stars. Gravity-bound accumulation defines planets. Kelt 9b reminds us that nature does not care about our categories. It only obeys physics, and physics allows for extremes. When we examine this planet carefully, we see that it sits at the intersection of several limits. The limit of irradiation a gas giant can endure, the limit of atmospheric stability under intense ultraviolet flux, the limit of orbital proximity before tidal disruption, the limit of temperature before molecular chemistry gives way to atomic dominance. It does not break these limits, but it approaches them. That makes it valuable. In science, the edges of parameter space are often the most informative. They test models. They reveal weaknesses in assumptions. They force refinement. Kelt 9b has already reshaped atmospheric modeling. Before ultra-hot Jupiters were studied in detail, many atmospheric models focused heavily on molecules like water vapor, methane, and carbon monoxide. But Kelt 9b's temperature regime requires models that emphasize atomic absorption, ionization, and high-energy radiative transfer. It bridges planetary atmospheres and stellar atmospheres. It pushes planetary science into regimes once reserved for stellar physics. And that is a quiet revolution. Another important lesson from Kelt 9b is about diversity. If one were to look only at our solar system, it would be easy to believe that gas giants are cold, distant, and composed of layered cloud bands. But the galaxy contains billions of stars. Around those stars, gravity arranges matter in countless configurations. Migration reshapes systems. Stellar type influences planetary environment. Chance interactions tilt orbits. The result is diversity beyond early expectation. Kelt 9b is not common, it is rare. But rarity does not reduce importance. Sometimes, rare systems teach the most. Because they occupy territory where theory is stretched. Because they illuminate processes that are subtle elsewhere. For example, atmospheric escape occurs in many exoplanets. But in Kelt 9b, escape is dramatic. Its high temperature makes hydrogen outflow easier to measure. It helps refine models that can later be applied to smaller planets, including rocky worlds around active stars. Understanding atmospheric loss in extreme gas giants informs our understanding of atmospheric retention on potentially habitable planets. Extreme systems provide clarity. There is also a philosophical aspect to this story. Kelt 9b orbits 670 light-years away. The light we analyze today left that system in the late 14th century. When that light began its journey, telescopes did not exist. The concept of exoplanets did not exist. Yet now, we dissect its spectrum, measure its atmospheric winds, detect vaporized iron. This transformation, from ignorance to detailed understanding, occurred in just a few decades. It reflects the rapid expansion of observational capability, from ground-based telescopes detecting brightness dips to space observatories analyzing infrared spectra to high-resolution spectrographs measuring atomic lines. Our tools have advanced dramatically. Kelt 9b was discovered only in 2016. Within less than a decade, it became one of the best characterized ultra-hot Jupiters. That pace of discovery suggests that even more extreme or unusual planets may await detection. Perhaps worlds orbiting hotter stars. Perhaps planets with unusual compositions. Perhaps objects straddling the brown dwarf boundary in unexpected ways. The galaxy is vast, and our sampling has only begun. Now return your thoughts to KELT 9b itself, a gas giant nearly 3 times Jupiter's mass, orbiting every 36 hours, locked in synchronous rotation. One hemisphere bathed in relentless ultraviolet radiation, iron vapor in its upper atmosphere, hydrogen escaping into space, supersonic winds redistributing heat, a magnetic field perhaps shaping outflow, a future likely ending in stellar engulfment. All of this unfolds quietly, steadily. There is no drama in real time, only gradual processes governed by equations. And yet, when viewed from afar, the story feels dramatic. A planet glowing like a small star, a star burning fast and bright, a system destined for transformation. Perhaps the most remarkable thing about Kelt 9b is not that it is hotter than some stars. It is that it exists at all. That planetary formation and migration can produce such a configuration. That gravity and radiation can balance in this way. That matter can endure such intensity without immediate destruction. It expands our mental map of what planets can be. Not only icy moons and temperate Earth-like worlds, not only gas giants with swirling clouds, but incandescent spheres of atomic gas circling blue-white suns. In the end, Kelt 9b reminds us that the universe is not constrained by our initial expectations. When we look beyond our solar system, we do not simply find variations of home, we find extremes. And those extremes teach us more than familiarity ever could. As we close this journey, Imagine that distant system once more. The blue-white star shines intensely. The planet races around it, completing another orbit. Its atmosphere glows. Its mass holds firm. Its future approaches quietly, written in stellar evolution. And across the darkness between stars, we watch, we measure, we learn. Because somewhere in Cygnus, a planet warmer than some stars continues its endless circuit. A reminder that even in the calm vastness of space, physics allows for astonishing intensity.